We're going to take a look at some application problems for linear differential equations. Now, the first couple we're going to look at, we're actually going to derive a few formulas that we saw way back in like pre-calculus. And those are our population growth and radioactive decay problems. Both of these problems are basically the exact same problem, just changing the notation a little bit. We saw, so let's take a look at the population growth. We saw way back in pre-calc that the population of at any given time is equal to the initial population, the population you start with, times e to the kt, where k is some growth constant. Now, the k depends on what type of problem you're talking about, right? Because different populations grow at different rates. If you're talking about the growth rate of a culture of bacteria, that's going to be a much larger number than if you're talking about the growth rate of human beings. So k's got to be determined for every single problem that you work with. But where did this problem actually come from? How did they get to here? Well, they started out with a very, very simple assumption. And they said the change in the population over time would be directly proportional to the population at that time. Well, let's see if that makes sense. One would expect where if you have a very small population, the overall population can't grow very much. But if you have a big population, then it can grow quite a bit. So this should make sense, right? The bigger the population is, the faster that it can grow. Well, this is a first order linear differential equation. Our dependent variable is p, our independent variable is t. So we can actually just separate our variables here a little bit. I'm going to move, of course, that differential to that side, so we get dp is equal to kp dt. And then you can move the k and the p to this side, but by convention, you kind of keep the k on that side. So we get dp over p is equal to k dt. Now we have all the p's on one side and all the t's on the other side. Remember, k is just a number. It's a constant based off of the rate that a population can grow. Now all we got to do to finish solving this is, well, integrate both sides. It's the integral of k dt. Well, this is just the natural log of the absolute value of p is equal to kt. All right, we can solve for p now, kind of. We would write this in exponential form, so let's see, this would be the absolute value of p is equal to e to the kt plus c. Now, I got a couple things to do to clean this up to get where we're going. Let's start by rewriting this side. And we've seen this in the past. I can write this as e to the kt times e to the c. Now, since c here is an arbitrary constant, e to an arbitrary constant is just another arbitrary constant. Now, just so I don't use the same letter, I'm going to call that for now c1. Now here I'm saying the absolute value of p, but if p is a population, well, it has to be a positive number, so I don't need the absolute values here. So we end up with this equation, c1 e to the kt. So we're almost there. We only would need one more significant piece of information to get the exact formula that we had in the past. To know how fast a population is going to grow, you have to know something about the population at a given time. Generally, we know something about an initial population, right? We set up a scenario, we see what's happening at the beginning to watch how fast it grows. So most of the time, let me move this up here, most of the time we know p of 0 is whatever the initial population is. So p sub 0 or p naught is our initial population. I'll put those up here in a second. So if we plug that in, notice what we end up with. Well, p of 0 is equal to c1 e to the k times 0, which is our initial population. So I get c1 is equal to p naught, right? Because that's just e to the 0, which is 1. So our function becomes p naught e to the kt. Well, our course here is p naught was the initial population, and k is a growth constant. All right, so there's the equation that you learned way back in pre-calc, and you see it's a very, very simple linear differential equation. Now, most of the homework problems that you run into in this section end up being pre-calculus type problems where you're just starting out with this formula. The good news is since I already solved it for you, you can start here. We also saw radioactive decay, and I'm not going to go through all this again because it ends up being exactly the same thing. Radioactive decay formula looks like this. The amount of material you have left after a given time is the original amount, e to the negative kt. Now, two things here. What is radioactive decay? Now, this isn't a physics class, so the real short, brief notation for this is if something's radioactive, it's giving away energy. It's emitting energy in terms of particles like alpha, gamma, and beta particles are coming off of, which means it can't sustain what it is since it's giving up some of itself, and it decays or changes into different elements. So, the amount of the original stuff, most books use something like uranium because we all know that that's radioactive. The amount of stuff you have left is the initial amount, e to the negative kt. Now notice this has almost the exact same form as our population growth. The only big difference you see here is a negative out front of the k. That's there to show that it's explicitly decaying. Technically, you could do the problem just like that. It's just the k you solve for would end up being a negative value. Some books put the negative there, some don't. Most of them do so they can see that it is decaying. So here, this would be the initial amount of stuff, and k here is the decay constant. Pointing at the k, not the t there. The k is your decay constant. Now, depending on how radioactive something is how much it's emitting energy as it sits there. The more energy it emits, the faster it decays, and the more radioactive it is. So for each different substance you have, k is going to differ. Now, the derivation is exactly the same because you see it's the exact same formula, so all this goes the same way. The only other thing that you would need for these problems, because again, now that you've kind of seen how to derive it, you can start with this, is something called half-life. The amount of time it takes for A to be equal to 1/2 A naught. Okay, basically all this says is how much time does it take to where if you started out with 100% uranium and it's decaying, turning into other stuff, how long does it take for where you only have half of the stuff is still uranium? So this is really what you're looking for, that the amount is equal to half the original amount. Because most of the time, you don't even have to be given the original amount to figure out problems for radioactive decay. All right, let's take a look at another example where we can apply a linear model for a real-world example, and this is called Newton's law of cooling. And the idea here is if you take something that, by the way, this works for heating too, but we're just going to stick with cooling. If you take something that's hotter than the environment that it's in, it's going to cool down. Now, can we come up with a formula that tells us what temperature the item will be after it's been in a specific environment for a given period of time? The answer is kind of. For this one, we're definitely going to have to make a whole bunch of assumptions. And by the way, these aren't 100% correct either. We made a few assumptions with the population growth and decay models. The real ones are a little bit more complicated, but these are fairly accurate. Newton's law of cooling, since we're talking about the transfer of heat, we have three different ways that we can conduct heat. We have conductive, that's when we're touching something. Convective when air's moving around, and radiation where heat's being emitted. This one really only takes a look at the radiation and not the convection or the conduction of heat. So it's not quite right. It works fairly well though for most environments. So here's the idea. Does it make sense that the rate that something's going to cool down depends on the difference between its temperature and the room's temperature? I'm just going to say the room or whatever environment it's in, right? If you take a glowing hot metal ingot and you put it in this room right here. Now we're assuming that the room's big enough to where it doesn't affect the overall temperature of the room either. It basically stays the same. it's going to cool a lot faster if this room is minus 100 degrees compared to if it's 1,000 degrees, right? So that difference in temperature is really what we're talking about. So let's let T be the temperature at time T. Let's let T sub m be the let's see T sub m be the medium temperature. That's basically the temperature of the environment that you're putting the object into. Well, does it make sense that the rate the temperature is going to change over time is going to be directly proportional to the difference in the temperature? All right, so let's take a look at this order here, because I could have done the difference the other way. We're assuming that this is cooling. So we're assuming that this is going to be a negative value on this side. So since the medium, or the temperature of the, I said that backwards. This thing's going to be cooling, then this here, we want this to be a positive value because the temperature of the object is bigger than the temperature of the medium. We want this to be decreasing. All right, so our independent variable is little t, our dependent variable is big T. Remember, K and Tm are constants. Now, K is a constant, again, that's specific to every problem that you're working with. And it really has to do with how fast the environment can transfer the heat, right? Air doesn't transfer heat as well as, say, water does. So if your medium was water, then K would be much bigger than it would be if, say, it was air or something like that. Well, we can separate our variables again. And again, let's just follow our steps like we normally do. This will be K, T minus Tm, dt. Let's put all the big T stuff to this side. So T minus Tm is equal to K dt. We're seeing a lot of the same things that we've seen before. Now, if we integrate both sides, on the left-hand side, remember our variables t, you could use a Hue substitution. Remember, this is just a constant, so it's kind of like if I said, what's the integral of 1 over x plus 3 dx, right? That's just the natural log of the absolute value of x plus 3. All right, so in this case, we're going to get the natural log of the absolute value of t minus tm is equal to e to the kt plus c. Sorry, skipping a step here. Doing that the next step. Kt plus c. All right, so now this is one of the reasons we wanted to keep this positive here, because I'm going to want to get rid of that absolute value, so I want to keep this as a positive value. So when we convert to our exponential form, again, we've kind of seen this before, I'm going to drop the absolute value because, again, we said that this was cooling, so that's positive. I get some constant e to the kt, so t is equal to Tm plus some C1 e to the kt. Okay, so there's our formula, except for we still have this arbitrary constant. Now remember, K is something that we can figure out from the environment that we're in, how fast it transfers heat energy, and we know the temperature of the medium. So the only constant here we have is this constant right here. Now again, you have to assume that you know something about the system that you set up. So we're going to assume that we know the original temperature of the object, right, when we put it into this environment. Now, if we plug that in, let's actually go way back over here. There's a little bit more room. We plug that in, so T of 0 is equal to Tm plus C1 e to the k times 0 is equal to T naught. That's 1, so we get Tm plus C1 is equal to T naught, or C1 is equal to T naught minus Tm. Well, plugging that back in, we get T sub m plus T naught minus T sub m e to the kt. All right, so there you go. Now, this ends up giving us the temperature at any given time. The only thing that you really need to figure out is the decay constant here. So just like the radioactive growth and decay problems and the population growth kind of things, I did all the work for you, so you can just use this formula. So if you're talking about some temperature of an object after a given time, just find the arbitrary constants for this problem and answer whatever questions you have. All right, let's take a look at one more type of problem that you're going to run into, and this one's a little bit more complicated. Mixture problems. Not quite the mixture problems we had in pre-calc type thing, but here's the idea. I'm going to use, I think what ZIL does a lot here. We're going to talk about saltwater tanks. Now, saltwater is a lot of times referred to as brine, so if you read a problem that says brine, all they mean is saltwater. Let's say that I have a tank here, and I'm pumping water into this tank, and there's some amount of water in it. And I'm also pumping water out of the tank. Let's say that there's some salt dissolved in the water here, and I'm pumping in some salty water here. And also, I'm pumping out some salty water. The question is, can you tell me how much actual physical salt is in the tank at any given time? And actually, you can. It's not that hard to do. And we're going to do this by using a good engineering technique called like dimensional analysis. We're going to look at what it would take. Well, let's take a look at this. So here's what I'm going to do. I'm going to go ahead and say, let's let A of T be the salt in the tank at time T. Okay, so if I let A be the amount of salt in the tank. So if I want to know the salt, if I knew this function, if I want to know the amount of salt after 10 minutes, I could plug in 10 and tell me how many pounds or whatever salt in there. To do that, it's actually easier to take a look at how fast the salt in the tank is changing. Well, first off, let's think about units here. Here we have an amount. An amount is something, I'm just going to pick some units and we're going to use something like pounds per, and this is time, something like seconds. So here we're going to have an amount over a time. So whatever we do on this side, we're going to have to end up with this same thing. So let's see, how fast is the salt changing? Well, let's talk about the part that's changing from us pumping it in. Well, the amount of salt we're putting in the tank kind of depends on two things, right? It depends on how fast you're pumping the water in and how much salt is in there. So it depends on your inflow rate and the density of your salt. Now, before I go any farther, let's see if this makes sense as far as our dimensions work. An inflow rate would be like we're pumping 2 gallons in per minute. So this would be something like gallons, since I have seconds over there, I'll use seconds, gallons per second. Inflow density. Well, density is what? It would be an amount over a volume. So this would be something like pounds per gallon. All right, now notice our gallons here are going to cancel out and we'd end up with pounds per second, and that's the set of units on this side. So at least dimensionally, our analysis here makes sense. So that's how we're changing the amount of salt by the stuff we're pumping in. How much are we changing the salt by how much we're pumping out? Well, that would be taking salt away, so that would give us a minus. Well, the same logic, that would have to be our outflow rate times our outflow density. Now again, since it's the same thing over there, we're going to get the same unit. So we're still going to end up with pounds per second minus pounds per second. It's going to tell us how fast the salt's changing in the tank. Now the good news for solving these problems, even though this looks difficult, most of this is generally given in a problem. The only part that ends up being difficult to find is the outflow density, and we'll take a look at that in a second. Let's just try a problem. So, let me get that. let's say that this is being pumped in at, let's do 3 gallons per minute, and it has, let's keep the numbers small. Let's say that it's 2 pounds per gallon. So we're pumping in water into this tank, and we're pumping in 3 gallons per minute, and we know we've already mixed in 2 pounds for every gallon, 2 pounds of salt for every gallon we pumped in. Let's say that our tank here is like, I don't care, 300 gallons. Doesn't matter in this case. And let's say that we're pumping water out here at a rate, let's do something different, 2 gallons per minute. Now, notice the inflow density I can tell you, because we would know what we were pumping into the tank. But since it's being pumped in the tank, and by the way, I haven't said it before, we're assuming this gets well mixed before it gets pumped out. It gets well mixed and then pumped out. Whatever is being pumped out here has the same density as the whole tank. But since I don't know what the density of the whole tank is, I don't know what the outflow density is specifically. So that's kind of like our unknown. So let's see if we can set up this problem with what we know. Well, I know, let's get that over there. The inflow rate, that's the gimme, that's 3 gallons. I'm just going to put the numbers in here. The inflow density is 2 pounds per gallon. Now notice here, this again is going to give me pounds per minute. I'm sorry, I was pointing the wrong way, pounds per minute. All right, outflow rate, we know the outflow rate, that's the same, that's going to be 2. But what is the outflow density? Well, remember, density is an amount divided by a volume. Well, how much salt is in the tank right now, at any time? Well, by definition, I just erased it. By definition, that's what A is. A tells us how much salt's in the tank. So this is how much salt's in the tank, divided by how much volume is in the tank. Well, we started out with a 300-gallon tank, 300 gallons in there. If we're pumping in 3 gallons, and if we were pumping out 3 gallons, then it would remain at 300 gallons. But since we're pumping in at one rate and pumping out at a different rate, the volume of this tank is changing, how much water or brine is in there. So how much is it changing by? Well, it's going to be our 300 gallons. And think about it, what's happening? Are we increasing or decreasing the volume of this tank? Well, since we're pumping out at a slower rate, the volume is increasing. And how much is it increasing by? By 1 gallon per minute. So this is going to be plus 300, 1 times T. Now, remember watch, I'm going to change this real quick and I'm going to change it back. If this had been 1 gallon, then there's a difference of 2 gallons per minute, and this would have been 2T. Right? If those would have been switched, if we were pumping in at 1 gallon and pumping out at 3 gallons, then that would have been minus 2T, because we would be decreasing it. But let's just stick with our 2 and 1. All right, let's just go ahead. Now I'm going to clean this up just a little bit. So we get dA dt is equal to 6 minus 2a over 300 plus t. All right, now remember, our dependent variable is a, our independent variable is t. So this is just a first order linear differential equation. So we're going to use an integrating factor. So I'm going to write it like this. I'm going to move this piece to the other side. And I'm going to write it more in our first order linear form. I'm going to do my integrating factor here, but I'm going to move it up over there to work. Our integrating factor, remember, is e to the integral of p of x dx. Now, of course, we're not using x's here, but it's the function in front of the dependent variable. So this is 2 over 300 plus t dt, or e to the 2 integral 1 over 300 plus t dt. All right, for here, you can use a Hue substitution to integrate that. That's just a logarithm. So here I get 2 natural log absolute value of 300 plus t. All right, so I can put up that 2 as an exponent and simplify. So this just gives me 300 plus t squared. Okay, so now remember, and this is the reason I told you to learn how to say it this way. What do we do with our integrating factor? We multiply through both sides by it, then integrate. On the left-hand side, we always get the integrating factor times the dependent variable. So on the left-hand side, I get my integrating factor times the dependent variable. On the right-hand side, I have to multiply and integrate. Okay, the right-hand side is just a Hue substitution again. So this is 300 plus t squared a. Hue substitution, that just ends up being u squared, so adding on the power, divide by the power, so divide by 3, so it's 2, 300 plus t cubed plus some constant. Now, of course, to solve for a, all I'd have to do is divide through by this. So my a of t would be 2 times 300 plus t plus c times 300 plus t to the negative 2. Okay, so there's basically our answer, but we still have an arbitrary constant here. To figure out what the arbitrary constant is, a lot of times, again, since we're setting up the problem, we may know something about the original amount of salt in the tank. Like we may know that it starts with, 10 pounds of salt. Right, if we're told that it starts with 10 pounds of salt, then basically what that gives us an initial condition. A of 0 would be 10. So you plug that in here, put in where there's a t, put in a 0, and then solve for c. Ooh, that's going to be an ugly number. I'm not doing it. Plug it in and see what you get. So once you solve your differential equation, then apply any initial condition that you get for them. So for each one of these mixture problems, it's always going to go with the exact same setup. So this line right here is going to be incredibly important for you to memorize. Inflow rate times inflow density minus outflow rate times outflow density. The outflow density is always the difficult part because it's the amount of salt in the tank at any given time, which is A, divided by the amount of salt in the tank. The denominator here is always going to be the original amount in the tank plus or minus the difference that it's being pumped in at. Other than that, it's a first order linear differential equation. Just use your integrating factor.